In this lecture video, I will discuss Sp2 and Sp1 hybridization, and we'll go over an example of molecules that have Sp2 and Sp1 hybridization in them. So first, let's now discuss Sp2 hybridization. So again, as its name implies, this refers to the fusion of one of the S and two of the 3p orbital. So there are 3p orbital. For many of the atoms that we look at on the second row, they have 3p orbital, but only 2 out of those 3p orbital are involved in the hybridization with the s orbital. So that basically means there's one p orbital remaining. And this p orbital remaining right here is normally used to form another type of bond that we call the pi bond. And this is basically what's seen in the double bond. And an atom with Sp2 hybridization has the trigonoplanar electron geometry. So we can then look for this electron geometry right here, and when we see it, then we know the atom must have Sp2 hybridization. And for an example, this molecule. So when we construct the Lewis structure of this molecule, this is what it would look like. And looking at each of this carbon right here, so this carbon right here basically have the trigonoplanar electron geometry. So this is trigonoplanar. And therefore, it must have had Sp2 hybridization. And the same thing is true for the other carbon. So this carbon is also Sp2 as well. And now let's construct what is happening. So in the case where the carbon undergo an Sp2 hybridization, and initially the orbital diagram of the carbon before hybridization took place is as follows. So here has 2s orbital with 2 electrons in it, and here's again the 2p orbital, and we're going to label this as 2px, 2py, 2pz, so we can distinguish among them. And in the case of Sp2 hybridization, only 2 out of the 3 p orbital are involved in this process. So basically, we are looking at the following. So the 2s is hybridizing with 2 of this 3p orbital, and this one right here, it remains unhybridized. And because now we have these 3 orbitals right here that are hybridized together, therefore we will produce 3 hybrid orbitals. And each of them will then be referred to as an Sp2 orbital. So there it is. And now we still have 1 p orbital remaining that is unhybridized. And that is this 2pz right here. And there are 4 electrons. So therefore each of the electron will then go to each of this orbital. So the energy gap between this Sp2 versus this 2pz orbital right here are very close with each other, and therefore that makes it possible for the electron to go into each of this orbital. And that's what it would look like. And now if we were to ask ourselves what is the structure of an Sp2 carbon would look like, then it looked the following. So it looked a little bit bigger and shorter, so a little bit fatter compared to the Sp3 orbital that we have seen previously already. So this is what each of this would then look like. And now each of them have 1 electron in it. And we still have the p orbital, this p orbital right here, that is remaining unhybridized. And as we have seen already, then the structure of the unhybridized p orbital would look like that. So there you go. That's what we would have. There are 4 orbitals, and again, this 4 orbitals right here meet together at the node, so they have to combine together at the node and somehow fit together. And the way to do that is basically by first having these 3 orbitals right here split out in way that are symmetrical first, and then we then put in this last remaining orbital. And when all of this orbital right here fuse together in that particular way, then the structure of the atom would then be symmetrical, and all of the orbital would have their electron as far apart from each other. And in the end, this is what it will look like. And that is the reason why that it would then have the trigonoplanar electron geometry. So I will construct this atom right here by first starting out with a trigonoplanar geometry. And here it is, trigonoplanar. And maybe we'll make this a bit shorter to make it look exactly trigonoplanar. And now each of the sp2 orbital will then go into each of this exit. So we have one that will then go right here with its electron, and the other one will then go on the other exit with electron, and then the other one go to the one on the back. So that's how the 3 sp2 orbital would be. And lastly, remaining, we still have one of the p orbital that is unhybridized, and I'm going to change this to red, and this red one right here will then go in here. And now you can see this is the way how all of the orbitals can be as far apart from each other and look symmetrical. And so this is what it would look like. So this is the structure of an sp2 carbon. And now in this molecule right here, we have 2 of this carbon, right? And now we can see that this is one carbon right here, and this could be the carbon on the left. And now this would then involve in bonding or overlapping with the other carbon that look also exactly similar to this. And so they overlap together to form the molecule. So let's now construct the structure of this molecule. And so I'm going to start drawing the other carbon by continuing from here. So starting from here, I'm going to construct another sp2 backbone, and I'm going to put in the orbital. So here we go. And now this orbital overlap with the other one to form a bond. And here is the other sp2 orbital, and here will then be the other sp2 orbital, and now the p orbital will then go in there, and here will then be the electron. So that's how the 2 carbons are overlapping together to form bond between them. And now we can see each of the carbon has 2 hydrogen on them. So how does this 2 hydrogen fit in? Then the answer is as following. So the hydrogen again will be using electron from its 1s orbital to overlap with this. So we have 1 hydrogen right here, and now the electron can pair together to form the bond between them. So let me go ahead and redraw this a little bit better. So let's create this back again. And now let's put in the hydrogen. So this is where the hydrogen would be. And now the electron from the hydrogen and the electron from the sp2 orbital of this carbon right here will overlap together to form that sigma bond. And same thing go over here as well. Here is the other hydrogen, and now the electron will get paired up. And same thing over here. And lastly, this one right here. So that's how we build in this 4 hydrogen that are connected to the 2 carbon. So what happened to this double bond right here? Where did this double bond come in? So here is how that double bond is being produced. So look at this p orbital right here. This p orbital right here has 1 electron in it, and this p orbital right here also have 1 electron in it. So technically speaking, whenever we have 2 orbital and they have unpaired electron in them, those orbitals would like to pair together, so that way they can form a bond, right? But in this case right here, these 2 orbitals, due to the position of this, they can actually not touch each other from end to end, but instead they have the tendencies, and we can see that this one tend to bend over a little bit, and this one right here tend to bend over a little bit, and together they will then be producing this double bond right here. So this double bond right here is basically formed by the overlapping of this p orbital and this p orbital right here over a distance, and they're not touching from end to end, but they kind of bend together a little bit, squeeze in a little bit, and this then produce that double bond. And as for the other bond, so this bond right here, so one of the bond in this double bond right here is the sigma bond, and that sigma bond right here get produced by this carbon using its sp2 orbital overlapping directly with the sp2 orbital from the other carbon. So let's now label all of this bond. So in this case right here, this bond right here is a sigma bond, and this is produced by the overlapping of the carbon using its sp2 orbital to the other carbon that is also using its sp2 orbital as well. And there we go, we have that first sigma bond. And now this other bond right here, so this bond right here is then referred to as a pi bond. So that's what we call this, a pi bond. And this pi bond right here is being produced by carbon using its 2pz orbital. So we can just simply say 2p, but to be more specific, we can also put in the axis, and that is on the z orientation, to the other carbon that is also using its 2pz axis as well. And that is basically the trick to the pi bond. In order for us to actually have this pi bond right here, we have to use the orbital that are on the same axis, so that way they can parallel with each other. And we can either use 2py and 2py, or 2px to 2px, but if we're going to be using 2pz, if we're using the z or the p orbital from the z axis in one carbon, we also have to use the same one from the other carbon. And now we have ourselves the pi bond. So this pi bond right here, it basically is a bond that is formed due to the side-by-side or parallel overlapping of the orbital. Okay, so side-by-side overlap rather than end-to-end. This is now side-by-side overlap of two orbitals in parallel orientation. And again, they have to be on the same axis, so that way they can be as close together as they possibly can be. And that when we'll be having a pi bond. Okay, and as you can imagine right here, in comparison between a sigma bond and a pi bond, the sigma bond is basically stronger compared to a pi bond. And the reason why is that because in the case of the sigma bond, the orbitals are actually touching each other end to end. So they basically meet and touch each other. And that's why they're stronger compared to another bond that is being produced over the distance. Okay, so please keep that in mind. Sigma bond tend to be stronger compared to the pi bond. And overall, this is the structure of acetylene. And now moving on to another example involving Sp1 hybridization. So in this case right here, Sp1 hybridization refers to the fusion of the s orbital with only one out of the 3p orbital. And so because only one of the p orbital are involved in the hybridization, there are basically 2p orbital remaining. And those 2p orbital are then used to form the 2 pi bond, similar to what we have seen already. And Sp hybridization, sometimes we call this Sp1, sometimes we simply just call Sp, and it will assume it will be Sp1. So Sp1 hybridization then have linear electron geometry. And this is the type of hybridization that is seen in triple bond. And now let's use an example. So here is acetylene right here, and when we draw the Lewis structure of this is what it would look like. So we can then see that this carbon right here have the linear electron geometry, and that would then imply that it must have undergone the Sp1 hybridization. And same thing, this carbon right here is also sp1 as well. And now, let's really look at the orbital diagram and see what's happening in sp1 hybridization. So here it is again for the carbon. Initially, here is a 2s orbital, and we have to use the valence orbital. We don't care about the 1s orbital, but only the 2s. So this would be the valence orbital. And here are the 3 2p orbital. Again, let's label them 2px, 2py, and 2pz. And it has 2 electrons in them. It doesn't matter where we put the electron. We can put electron in any of these 3p orbital right here. And in the sp1 hybridization, then we will then see that only one of the p orbital is involved in the hybridization with the 2s orbital. So here it is, and now we will have 2 hybrid orbital, and we'll label each of this as sp1 and sp1. And we will still have 2 p orbital remaining that are unhybridized, and that would then be the 2py and the 2pz. And now, energy-wise, they are quite similar in energy, and that makes it possible for the 4 electrons to go into each of this orbital. And that's how we would have it. And as for the structure of the sp1 orbital, the sp1 is basically shorter and it's basically fatter compared to the sp2 and sp3. So in comparison, maybe I will draw this right here so you can see the comparison between sp1, sp2, and sp3. So in sp1, it's short, or we can call this short and fat, and versus an sp2, it's a little bit longer. And now the sp3 would be the longest one. So this is sp1 and sp2 and sp3. And here would be the node where the nucleus of the atom would locate at. So that would be the comparison between sp1, sp2, and sp3. And in this case, we have 2 of them. Now, don't forget that we still have here 2 remaining p orbitals that are unhybridized. And the structure of the unhybridized p orbital is something we have seen already before. It consists of the 2 lobes that are equal, that look exactly the same thing. And now we have 4 electrons in them. Okay. And now because this particular atom right here, and with this type of hybridization, they have these 2 orbitals that are the same, and these 2 orbitals right here that are the same. And they have to fuse together because this is the node where the nucleus of the atom would be. So how do all of this fit together? So that way, the electron would be symmetrical and distributed as far as they possibly can from each other. And that's why they will have to adopt the linear geometry. Because in the linear geometry, here's what happened right here. So I'm going to first start by drawing the linear backbone. And so first, these 2 hybrid orbital right here, one of it would then go into one of this, and the other one would then go into the, so let me change color. So the other one, we look the same thing, and now lay on the other end. And now it has electron in it. So that's how the sp orbital would be. So that way it can be symmetrical. And as for the 2 remaining p orbital, then this is where they would go right here. So we still have the y and the z orientation. And so I'm going to draw this. So one of the p orbital will be going in this y-axis, and the other one will then go into this z-axis right here. And now each of it will have 1 electron in there. So that's what the sp carbon would look like. And now we have 2 of it. So in fact, let me actually change color so we can keep track of this easily. And so let's see, well, let's go ahead and color one of it. So this is one carbon. And now in the structure of this molecule, acetylene, then we have two carbon and both of them are sp1. So essentially, there will be another one like this that look exactly the same. So let's go ahead and draw them in. So again, I'm going to start by drawing the other carbon by starting with a linear geometry. And now I'm going to put in the first one. So let's go ahead and keep the color coding, so the same thing. And the other one would then be in red. And now we can see that these two orbitals right here, maybe I should have drawn them a little bit closer together. But now the electron in them would then be shared. So this two electron right here would then be shared, and then that produce the bond between them. And now let's draw the other exit. And one of them, and this is where the p orbital, the unhybridized p orbital would be. And again, I will highlight one of them in yellow so we can see them. So in the end, that's what it would look like. And now we can see that the carbon is forming a bond with the hydrogen, right? And it turned out this bond right here would then be the sigma bond. And so for this carbon, so let's put in the electron in here. So this carbon is now overlapping with the hydrogen. And then that forms one of the sigma bond between the carbon and the hydrogen. And on the other end, there's another hydrogen, and that overlap with the other carbon, with the other hydrogen from the other sigma bond. And here is another sigma bond that are being produced by the overlapping of the sp1 orbital from this carbon and the sp1 orbital from the other carbon. So now let's label them. So this bond right here, this is a sigma bond that is formed by a carbon using its sp1 orbital to the hydrogen using its 1s orbital. And that's the same thing over here too. This is also a sigma bond that is formed by a carbon using its sp1 orbital to the hydrogen using its 1s orbital. And now here is another sigma bond. So there is a sigma bond right here. And this is the sigma bond that is formed between the two carbon. And involving, so the carbon will be using the sp1 orbital to overlap together to form that sigma bond. Okay. So where did the triple bond come in? Then here is what happened right here. So the p orbital, so let's say this p orbital right here that is highlighted in yellow, and this p orbital right here are parallel, and they have electron in them. So you can imagine they can actually form over the distance, and then that produce basically the first double bond between these two carbon right here. Okay, so let's change this into yellow, and we can see this can overlap over the distance, and then that forms the first pi bond. Again, this will be a pi bond. Now, the other pi bond will then be being produced by the other p orbital. So this p orbital right here and this p orbital here are also parallel as well, and they have electron in them, and so therefore they can also come together to now produce another pi bond. So that is what happened. So in the case of the of a triple bond, there's one sigma bond and two pi bond. And now let's label this pi bond right here. So this pi bond, so let's go ahead and label this pi bond involving the orbital, the p orbital in yellow. So this is a pi bond that is basically produced by carbon using its 2p y orbital to the other carbon using its 2p y orbital. Okay, and now the other one in blue, so this is another pi bond, and this involves one carbon using its 2pz orbital to the other carbon. They also using its 2pz orbital as well. So again, make sure we stay consistent. Is z to z and y to y. So that is what the structure of acetylene would be using this valence bond theory. And so notice the following: the rotation about the pi bond is not possible because that would then require breaking the pi bond. So due to the formation of this double bond right here, and because this is a bond and they stable this way, so that way these two orbitals right here can overlap. If we were to rotate, that basically means this pi bond right here has to be broken in order for the rotation to be possible. And this is why that whenever we have a pi bond that being produced by between two atoms, that restricts the rotation of that bond. So rotation is not possible in the case of a double or triple bond because of the pi bonds that been produced between the atoms.